NENOMATICA, where mathematics meets YouTube excellence. We will prove the identity that the floor of 2x equals the floor of x plus the floor of x plus 1/2, assuming x is between 0 inclusive and 1 exclusive. First, recall the floor function definition. If n is an integer and n is less than or equal to x, and x is less than n plus 1, then the floor of x equals n. Step 1. Analyze case 1 for 0 less than or equal to x strictly less than 1/2. On a number line from 0 to 1, we color the left half. Here is a quick challenge. If x equals 0.4, what is the floor of 2x? For this interval, we have the floor of x equals 0. Also, 1/2 is less than or equal to x plus 1/2, which is less than 1, so the floor of x plus 1/2 equals 0. And 0 is less than or equal to 2x, which is less than 1, so the floor of 2x equals 0. Substituting gives 0 equals 0 plus 0, so the identity holds in case 1. Next, remember a useful property for the floor function with integer shifts. The floor of x plus n equals the floor of x plus n for any integer n. Step 2. Analyze case 2 for 1/2 less than or equal to x strictly less than 1. On our number line, we now focus on the right half. In this interval, the floor of x is still 0 because x is less than 1. But x plus 1/2 is at least 1 and less than 3/2, so the floor of x plus 1/2 equals 1. Also, 2x is at least 1 and less than 2, so the floor of 2x equals 1. Substituting gives 1 equals 0 plus 1, so the identity holds in case 2 as well. This special case is part of a beautiful and more general identity, often called Hermite's identity. The floor of nx equals the sum of floors from the floor of x up to the floor of x plus n minus 1 over n, for integer n at least 1. Step 3. Generalize the result for any positive integer, n. Therefore, combining both cases, for x between 0 inclusive and 1 exclusive, we have shown that the floor of 2x equals the floor of x plus the floor of x plus 1/2. Quick challenge. Can you expand the floor of 3x using the general identity? Take a moment to think about it. Example. Our goal is to find a closed form for the alternating series s sub n equals 1 minus 2 plus 3 minus 4 plus plus parenthesis negative 1 to the power n minus 1 times n. Step 1. Observe the pattern for small values of n. Quick challenge. What is s sub 4? Compute s sub 1 through s sub 6. We get s1 equals 1, s2 equals negative 1, s3 equals 2, s4 equals negative 2, s5 equals 3, s6 equals negative 3. The results alternate in sign and grow by ones in magnitude. Step 2. Relate values to the floor function. Notice ones appear as the floor of n plus 1 over 2 for consecutive n. This suggests a compact formula with the alternating sign factor. Step 3. Set up mathematical induction. Induction hypothesis. Assume s sub k equals parenthesis negative 1 to the power k minus 1 times the floor of k plus 1 over 2. Induction goal. Show that s sub k plus 1 equals parenthesis negative 1 to the power k times the floor of k plus 2 over 2. Step 4. Transform s sub k plus 1 using the definition. S sub k plus 1 equals s sub k plus parenthesis negative 1 to the power k times k plus 1. Substitute the hypothesis. Factor out negative 1 to the power k and isolate the changing orange part. Step 5. Apply the floor identity with n replaced by k plus 1. The floor of k plus 1 over 2 plus the floor of k plus 2 over 2 equals k plus 1. Therefore, k plus 1 minus the floor of k plus 1 over 2 equals the floor of k plus 2 over 2. Substitute back to get s sub k plus 1 equals parenthesis negative 1 to the power k times the floor of k plus 2 over 2. Of k plus 2 over 2. The induction is complete. Therefore, for every natural number n, s sub n equals parenthesis negative 1 to the power n minus 1 times the floor of n plus 1 over 2. Welcome! In this example, we will solve a floor function sum using a clean, telescoping strategy guided by Hermite's identity. First, let's show the example. Then we will outline the rule we will use and proceed step by step, keeping the visual math clear and intuitive. Here is the key rule. we will use throughout. It is a floor function identity, often attributed to Hermite. We'll place it on screen now. Step 1. Rewrite each fraction to separate the constant 1/2 from the variable part. We'll show the step title. And now the rewritten sum. Quick challenge. Can you see how each fraction was split? For instance, n plus 2 over 4 equals n over 4 plus 1/2. Step 2. Apply the recall identity to each bracket, with x equal to n over 2 to the I for each term. We'll show the step title. Then, a brief expansion reminder. Now, the telescoping form appears. Tip: notice how the plus floor of 2x in one term is the minus floor of x in the next. Step 3. Use telescoping to cancel the middle terms. We'll show the step title. Then, the telescoping rule box. And show the simplified result that only the first and last terms remain. Step 4. If k is large enough, the last floor becomes 0. Then the sum reduces to floor of n. We'll show the step title. Now write the last floor as 0, and conclude the value is floor of n. Since n is an integer, floor of n equals n. That's our final result. In this lesson, we will solve a beautiful telescoping sum with floor functions. We will compute the sum S, defined by floor of x plus 1 over 2, plus floor of x plus 2 over 4, plus floor of x plus 4 over 8, and so on. We'll build the intuition, prove a clean identity, and finish with a simple case distinction for the final answer. First observation. For large n, each term becomes tiny. Write the nth term like this: floor of x over 2 to the n plus 1/2. As n grows, the absolute value of x over 2 to the n becomes smaller than 1/2. That pushes the inside between 0 and 1, so its floor is 0. This shows the series only has finitely many non-zero terms. The key identity. There is a handy relation for floor functions. Floor of t plus floor of t plus 1/2 equals floor of 2t. We rearrange it to get floor of t plus 1/2 equals floor of 2t minus floor of t. Now substitute t equals x over 2 to the n. That turns each term into a difference of 2 floors. So the sum will telescope. Let's rewrite the first few terms using the identity, so we see the cancellations. For n equals 1, we get floor of x minus floor of x over 2. For n equals 2, floor of x over 2 minus floor of x over 4. For n equals 3, floor of x over 4 minus floor of x over 8. Notice how everything in the middle cancels, leaving just floor of x minus floor of x over 2 to the k for the first k terms. Now let k go to infinity. We only need the behavior of floor of x over 2 to the k. If x is non-negative, then x over 2 to the k is a tiny non-negative number for large k, so its floor is 0. If x is negative, then x over 2 to the k is a tiny negative number, like minus 0.001, so its floor is -1. Therefore, the sum S equals floor of x for non-negative x, and equals floor of x plus 1 for negative x. Let's check with 2 quick examples to build intuition. Example 1. X equals 5.7. We compute the first few terms and add them. The sum equals floor of x, which is 5. Example 2. X equals -2.3. The partial sum stabilizes at floor of x plus 1, which is -2. These checks match our formula perfectly. Summary. We recognized that each term is floor of t plus 1/2. We used the identity floor of t plus 1/2 equals floor of 2t minus floor of t to create a telescoping series. The sum collapses to floor of x minus floor of x over 2 to the n, which approaches either floor of x or floor of x plus 1, depending on the sign of x. That's the final, compact result. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.